We need an efficient language for communicating mathematical relationships. This is our motivation for introducing variables and functions. Functions are like basic sentences that we can compose to tell stories and draw conclusions. That's literally the word for putting functions together, compose. Among functions that can be composed are those that undo each other. By thinking about how functions can undo each other, we will get our first glimpse of the imaginary number I, the root of -1. You want to teach your friend that the duration of travel increases in proportion to the distance traveled. If your friend requests that you use concrete numbers, you are forced to give a variety of examples, such as 20 meters divided by 10 meters per second equals 2 seconds, 50 meters divided by 10 meters per second equals 5 seconds, and 70 meters divided by 10 meters per second equals 7 seconds. This is tiresome and redundant because we repeatedly calculate particular examples of duration corresponding to particular examples of distance divided by particular examples of speed. Allow t to be a specific and particular value drawn arbitrarily from the non-negative numbers representing the number of seconds of travel. Let x be a specific and particular value drawn arbitrarily from the non-negative numbers representing the distance traveled in meters, and let v be a specific and particular value drawn arbitrarily from the non-negative numbers representing speed in meters per second. This way we collapse a multitude of examples into a single expression. When we place t, x, and v next to highlighted regions of number lines and then write down the equation t equals x over v, we do not mean that the entire yellow highlighted region of the number line is the entire orange highlighted region divided by the entire cyan highlighted region. We have not yet given meaning to the idea of dividing two number line regions. When we say t equals x over v, we mean that t is an arbitrary yet specific and particular example of a duration measured in seconds whose number value is chosen from the highlighted domain below, that x is an arbitrary yet specific and particular example of a distance measured in meters whose number value is chosen from this highlighted domain below, that v is an arbitrary yet specific and particular example of a speed measured in meters per second whose number value is chosen from this highlighted domain below, and finally, that we are bringing to attention the various specific collections of three numbers whose particular x, particular v, and particular t satisfy the condition t equals x over v. While it might seem obvious to think of t, x, and v as particular values, failing to emphasize this language now is a shortcut that leads to catastrophe during calculus. An equation is only the tip of the iceberg. Equations are often accompanied by physical or visual pictures. Fine print defining and limiting the context of an expression lurks beneath the surface. If a reader deems an equation in a physics or mathematics textbook sufficiently important to require memorization, the reader should also have at minimum a vague sense of the arguments that give the equation meaning, if not also facility in immediately regenerating such derivations. We've just seen that variables help us concisely write down relationships between collections of numbers. In the next section, we will describe a category of relationships called functions. One of the most important tools we have for illustrating theoretical models is the ability to plot functions. In this slide, we will enumerate the ingredients of a function. Domain big X and codomain big Y are both collections of numbers. A number indicated by a blue dot in domain big X and precisely one number indicated by an orange dot in codomain big Y are associated, as illustrated with a pink arrow. Other blue dots in domain big X are also associated according to their own pink arrows, each to precisely one orange dot in codomain big Y. All blue dots in domain big X correspond to some number in codomain big Y, though perhaps not all numbers in codomain big Y are associated with a number in domain big X. Little x is an arbitrary yet specific and particular object from collection big X. Y equals f on x is the particular resulting object in collection big Y. X f on x is called an ordered pair. It is the particular association between the little x and little y being discussed. The collection of all these pink arrows is called the graph big F, and finally, the entire picture painted by the combination of the domain big X, the graph big F, and the codomain big Y is, as a whole, called the function little f. For brevity during routine conversation, we will sometimes drop the prefixes big and little. F on x and the function f are different. F on x is the particular value that is associated, according to the function f, with x, itself a number at once arbitrary yet specific and particular. We will relax this strict language in the next slide. Thus far, the function f has referred to an arbitrary yet specific and particular relationship. In this example, we let f be the squaring function, defined as follows. We will allow its domain x to be all values, that's including negative, positive, and also 0 on the number line. We let its codomain y be all values, negative and positive and also 0 on the number line as well. And we describe the graph f using the association rule that says that y, in other words f on x, equals the result of the arithmetic procedure x squared. The ordered pairs in the graph f include 0, 0, 1, 1, 2, 4, and negative 2, 4. The plot of f on x versus x is called a parabola. In physics and engineering, we routinely use the phrase function f to refer specifically to the association rule, ordered pairs, or the plot of f on x versus x. But it might be helpful when speaking to mathematicians to remember that the word function can also refer to an entire picture including a domain and a codomain. F on x is not a function. F on x is not the function f. F on x and the function f are different. F on x is the particular value that is associated, according to the function f, with x, which is itself a number at once arbitrary yet specific and particular. Depending on the discipline, language may be relaxed so that the phrases function f, association rule f on x, and plot of f on x versus x are used interchangeably. We've just seen that a function contains a relationship between a domain and a codomain, between a source and a target if you would like. Functions and their plots are like basic sentences that we can combine to tell stories and draw conclusions in theoretical modeling. Learning about functions feels like learning about sentences. For functions, we draw domains, codomains, and arrows. For sentences, we diagram subjects, objects, and verbs. It can be as exciting to learn about functions as it is to learn about sentences. In this section, we show how these sentences can be combined, in other words, how functions can be composed. Alongside the function f, we now consider another function g with domain big Y, graph big G, and codomain big Z. We use the letter capital Y to refer both to the codomain of function f and the domain of function g, so that we can easily illustrate the process of composing functions, which looks like connecting a power plug into an extension cord. The composite object can be thought of as a single function that relates blue dots in domain x with green dots in codomain z. Little x is an arbitrary yet specific and particular number in domain big X that corresponds to the particular object little z, which equals g on f on x. The function can be read g circle f or g after f, and we could call the graph of g circle f. In this example, we allow domain x, codomain y, and codomain z each to refer to the entire number line. The graph f will be described by the relationship y, in other words f on x equals x squared, and the graph g will be described by the association rule for z, that is to say g on y equals y plus 1. Examples of ordered pairs include 0, 1, 2, 5, and negative 2, 5, producing a vertically shifted parabola. The idea of composing functions allows us to define a relationship between pairs of functions that becomes useful in later video tutorials. This is the concept of inverse functions. Consider the special situation in which the domain of function f is the same as the codomain of function g, and moreover, each blue dot lands in codomain x in the same place that it starts in domain x. For example, let big X, big Y, and once again, big X each to refer to the entire number line. The function f has some association rule, do quote-unquote something, and the function g has an association rule that is quote-unquote undo something. A point in domain x lands at exactly the same point in codomain x wherever the corresponding point in codomain y might happen to fall. In this situation, the functions f and g are called each other's inverses, and the plot of the composite function g after f is a diagonal line. It is useful to be able to recognize inverse functions by visual inspection of plotted curves. Suppose that the plot of f on x versus x looks like this. This is little y versus little x. What do you think the plot of g on x versus f on x will look like? Please pause the video to consider for a moment. Ready? Okay. Consider the ordered pair xy equals 3, 4. It corresponds to another ordered pair yx equals 4, 3. Every ordered pair xy in the upper plot corresponds to an ordered pair yx in the lower plot with the numerical values exchanged or flipped diagonally across the dotted line. The plot of g on f on x versus f on x is a mirror image of the plot of f on x versus x. Inverse functions are reflections about the dotted line y equals x. By thinking about the inverse of the squaring function, we will make our first acquaintance with the imaginary number I. In future video tutorials, the imaginary root will help us describe dynamics in oscillatory systems. Let the association rule inside function f be f on x equals x squared. We will let the function g have the association rule g on y equals the result of undoing squaring, which is usually called taking the square root. Something bad happens. Notice that, for example, -2 and 2 in domain x both correspond to the value 4 in codomain y. Thus, it is impossible to determine, given only the value 4 in domain y, whether to return the value -2 or instead +2 in the codomain x. If we insist on defining our squaring function in the context of a domain that extends across both positive and negative portions of the number line, the inverse function does not exist. Reflecting the pink plot of f on x versus x across the dotted diagonal generates the purple plot we are hoping to call g on y versus y. However, the purple curve is, in many places, double-valued, rather than providing one unique output as required for g on y to be a function. The object that we insinuate is a function by using notation such as g open parenthesis y closed parenthesis g on y is, in fact, not a function. Let us rescue the purple plot so that it can be thought of as the plot of a function with the entire number line as its domain. We will construct the square root function that many people work with as a sort of inverse of squaring. To convert the double-valued plot into a single-valued plot, simply neglect the lower branch. The resulting object now has everywhere no more than one value. Unfortunately, when evaluated at negative values of y, it has no value. That's not to say that the object has a value of nothing or of 0. It does not even have the value 0. The discussion on the following slide will construct values of g on y for negative values of y. We will relabel the north-south axis as the real part of g on y. We will add an east-west axis called I times the imaginary part of g on y, with east pointing out of the page toward the viewer. The values on the east-west number line are multiples of the object I. The square with edges I and 1 touches at two corners a new curve that is a rotation of the old curve we originally plotted in the vertical plane. The new curve lies in the horizontal plane. The horizontal plane contains the y-axis and the axis labeled I times the imaginary part of g on y. By defining I as the object that, when encountered in a square, returns -1, we ensure that the complicated three-dimensional curve we have just constructed becomes the dotted diagonal line after being squared. The dotted line lies in the vertical plane that contains the axis labeled the real part of g on y and the y-axis. The squaring function is the so-called undo button for this square root function that we have constructed, here called g on y, that being the real part of g on y plus I times the imaginary part of g on y. In this video, we have shown how variables can help us express mathematical relationships concisely, we have introduced functions, and we have provided a first glimpse into the imaginary root I. Such mathematical grammar provides a foundation for mathematical language arts in later tutorials.